Hey students, wanted to create this quick video for you all, just recapping the lesson I did about carbon earlier today. In the future, I will make sure to record over Zoom so you have these sooner. But to recap, I talked about carbon and its centrality in biological molecules. I started off this lesson by showing you a slide containing the four atoms that comprise about 96% of biological molecules: hydrogen, carbon, nitrogen, and oxygen. What we need to know is that these different atoms, they have different properties, and that's largely due to the electrons found in their outermost shells. We call those valence electrons. Hydrogen, for example, has one valence electron. Oxygen has 6. Now, what you need to know is when you see these diagrams, these represent electron shells. And electron shells, we usually in this class are only going to see the first two, although there are many other shells for other elements. But what you need to know is that this first shell, it can only hold up to 2 electrons. Once that shell is filled, it'll move on to the second shell, which can hold up to 8. So the reason that's useful is because atoms tend to follow what's called the octet rule, which means that they want to, or it's more favorable when they're in a molecule that allows their valence shell, their outermost shell, to be full. In other words, for carbon, nitrogen, and oxygen, when they have 8, and that's where the name octet rule comes from. When these have 8 total electrons in their outermost shell, that atom is stable in that molecule. The only exception is hydrogen. Hydrogen just doesn't have that many electrons. It only has 1. So to fill its outermost shell, it just needs 1 more for a total of 2. Other thing I mentioned was that these atoms, they have different electronegativities. I've ordered them from least to greatest electronegativity. I also mentioned that hydrogen and carbon, they have very similar electronegativities. And so whenever you see a hydrogen-carbon bond, which are common, those are actually non-polar. And that's because the difference between the electronegativities isn't big enough to give the properties associated with a polar bond. Okay? So carbon-hydrogen bonds are always non-polar covalent. All other bonds between atoms on this diagram will likely be polar. So for example, hydrogen connected to nitrogen, or hydrogen with oxygen, or even carbon with nitrogen and oxygen, those will be polar. Even nitrogen and oxygen will be slightly polar, with oxygen being the most electronegative. Okay. All right, so we can think about this because we can make predictions and understand the structure of biological molecules with this idea of valence in mind. Okay. Now, when you see just the term valence, that actually refers to how many bonds can be formed. And that corresponds to the number of valence electrons. So for example, nitrogen has a valence of 3 because it has 5 valence electrons, which means it needs 3 more, which can be gained through bonds, in order to fill that octet rule. Okay. So carbon is the most central atom in all biological molecules. Sorry about that. Because it has the highest valence, it allows for the most flexibility in building molecules. It has a valence of 4. And so when you think of carbon, you need to know that at most it can form a total of 4 bonds. For example, carbon often readily bonds with carbon in these single non-polar covalent bonds, where hydrogens, they share that 1 electron with the carbon, so that a molecule like this, which is methane, CH4, results in hydrogen having its outermost shell filled and carbon having its outermost shell filled. Something like carbon dioxide can also be an example. If you notice this carbon in the middle, it has a total of 4 bonds. Whenever you see lines, that represents a pair of electrons being shared. And this case, a polar covalent bond. And if you notice, carbon has a total of 1, 2, 3, 4 bonds, which fills its octet rule. Oxygen, if you remember, has a valence of 2, so all it needs is 2 additional electrons, which is why it has 2 bonds here. And same thing over here. Okay. Now, when you look at a lot of molecules in this class, you're going to see 2 different types of structures. You kind of see the long form, which is where we connect, for example, in butane, we connect 4 carbons, and the rest of the bonds are with hydrogens. Notice that each carbon in this chain, it's got 4 bonds connected to it. Isobutane, which has the same chemical formula, but different structure, we call that an isomer. It has this branch structure instead of a linear structure. And that's really representative of the flexibility of carbon. It can form all of these different types of structures. Okay. But what you're also going to see are these things called stick diagrams or stick chemical diagrams. This is the structural formula of butane. So this corresponds to this. The way you interpret this is every time you see an end of a line or a corner of a line, that's a carbon. So we have 1, 2, 3, 4 carbons. And same thing right here, you've got 1, 2, 3, 4. Now the difference is that they don't represent hydrogens. But if you don't see any other atoms connected, remember that carbon, in order to be stable in that molecule, has to have its valence shell filled. And so it's assumed that there are 3 carbon-hydrogen bonds attached to this carbon. Okay. So the last thing that we did in class is I asked you to look at this molecule called penguinone, and I asked you to find the chemical formula. And the way that you do that is you first got to identify what are the 3 types of molecules here, where you have carbon, hydrogen, and oxygen that are making up this molecule. Now, oxygen is the easy one, right? Oxygen contains, there's just one of those oxygens in this molecule. But let's start counting the carbons. So remember, any end or corner of a line is a carbon. So let's start here. We've got 1 there, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 carbons in this molecule. Now those double lines, those represent, just like up here, they represent double covalent bonds. So we need to keep that in mind when we start counting the hydrogens. So let's start with this carbon right here. Remember that carbon has to have a total of 4 bonds to have its valence shell filled. So this carbon right here is going to be attached to 3 hydrogens. Same with this carbon right here. And same with this one. And this one. If you're asking how did I get that? Well, let's look at this now. This carbon now has 1, 2, 3, 4 covalent bonds, making it stable. Now it has a total of 8 electrons in its outermost shell. Okay, so that's 12. Let's move on to these inner carbons. Let's look at this one right here. So this one has 1 bond there, 2 bonds, and this is where that double bond is important. We have 1, 2. So this one actually has 4 bonds connected to it, so it's already full. Same thing over here. Okay. Now this one right here, it has 1, 2, 3 bonds connected to it. So this carbon has a hydrogen hanging off of it. And same thing over here, since it's symmetrical. And this last carbon, it has 1, 2, 3, 4 bonds, so it's already full. So in total, how many hydrogens do we have? We have 1, 2 plus 12 is 14 hydrogens. So that's how we can use this idea of carbon having a valence of 4 to interpret the chemical formula of a diagram. I hope that was helpful. again, if you have any questions, reach out to me, and I will also be having that chem review session on Tuesday next week at 2:30. Have a wonderful weekend. I will talk to you all soon.